Let's take a look at sound waves. And to start off, we're going to talk about waves in different dimensions. All right, so we need to talk about one-dimensional, two-dimensional, and three-dimensional waves. So one-dimensional waves would only occur in something that only has a length. The wave can travel in one direction. In only one direction. Okay, so you can think about this as a one-dimensional object is a line. There's a one-dimensional object. And the only one-dimensional object we have is a rope. That's really easy to work with. A rope can have a wave running through it. That wave can only go down the length of the rope, and the wave can go back. It can only move in one direction, in one dimension, this way and this way. Right, so you're holding onto the rope here, you give it a flick, the wave goes down the rope and comes back. The wave can only go in one direction, basically. I mean, technically it's two directions, but it's one direction backwards and forwards. So a rope is a one-dimensional wave, a wave on a rope. A two-dimensional wave, this here has a length and width. Think area. The wave travels along a surface. And can go in many directions along the surface. And can go in any direction. And the wave can travel in any direction along the surface. So you're thinking two-dimensional is kind of like area. You've got a width and a length. Now you can think of a water wave. And if we look at a water wave kind of from the top, so let's imagine that we've got a lake here that we're looking at from the top. The lake is a two-dimensional figure. The surface, the lake surface, is two-dimensional. We can have a wave, right? Let's say there's a motorboat on the lake. We're looking at this from the top view. So there's the motorboat. And the motorboat has a wake that travels out like this. And the wave can travel in this direction. The wave can travel in this direction. Right, so we've got a motorboat here. And so those are two directions, and the waves travel along the surface, in any direction along the surface. So we've got our wake. It's traveling those directions. So two-dimensional surface. You can think of a water wave. A water wave on the surface of a lake. So the wave can travel in two different directions or in any combination of those two directions. A 3D wave has length, width, and height. So you think about it in a box. My beautiful three-dimensional cube. It's got a length, a width, and a height. So the wave can travel anywhere around there. Sound is a three-dimensional wave. It travels in all directions. All three directions. All right, now, before we get on, because we have a couple topics, we need to define kind of what a sound wave is. And we'll do that right before we talk about wave velocity and mediums. All right, so let's go back to our one drawing that we had. And we'll talk about okay, so sound, I'm just going to write it right here. What color am I going to use that? Red. Sound is a compression wave. In a physical medium. That medium can be air, it can be steel, it can be water, doesn't matter. So we're going to draw this picture again. We've got a speaker like this. There's my speaker cone. There's the magnet. Now the speaker cone vibrates back and forth. And we get a series of high pressure air, high pressure, followed by a low pressure, followed by a high pressure, followed by a low pressure, followed by a high pressure, like this. So the air particles in the high pressure are close together. They're very tightly packed. And then as you get to the low pressure, the air particles are much wider spaced apart. And then they become spaced close again in the high pressure. And then the particles are kind of spaced apart again. They spread out in the low pressure. And then it joins up and it becomes a high pressure again. So you can see this high pressure area of air molecules followed by low pressure, followed by high pressure, followed by low pressure, followed by high pressure. These are, so the high pressure area is a pressure of compression. Its pressure is higher than the ambient air pressure, and the low area is called rarefaction. It's an area of pressure lower than the ambient pressure. Now, how your ears work is quite interesting because your ears, inside your ears, you have something called your eardrum, your tympanic membrane. And when the sound waves, and I'm just going to represent sound waves like this. When the sound waves hit your eardrum, your eardrum itself, it's a little flap of skin type thing. It's a little membrane. So the eardrum vibrates back and forth. It vibrates in sync with the pressure waves hitting it. See, with this sound wave hitting your eardrum, which then vibrates back and forth. Then as your eardrum is vibrating back and forth, there's a few small bones that it vibrates. So I don't know what they look like, but we're just going to draw them in a certain way. There's a few small bones that vibrates. The stirrup, the anvil, and the hammer. These tiny bones vibrate. Right? Because the eardrum is vibrating and it's pushing on these bones, and these bones are vibrating. The one bone, the hammer, is pressing on something called the cochlea. The cochlea is a spiral shaped No, my drawings are really poor, but. And it presses, this bone vibrates up and down on this cochlea. And inside the cochlea, what happens is fluid is moving around. So you've got fluid. Then you've got little hairs growing inside the cochlea. These little hairs, so the fluid in the cochlea starts to vibrate, starts to get pumped around. The hairs start to vibrate. The hairs are attached to nerve cells. So we've got these little hairs, and these hairs vibrate. And when the hair vibrates, it triggers the nerve cell. And the nerve cell sends a signal to the brain that these hairs are vibrating. Now, the different hairs will start to activate at different times depending on the frequency that it's being pushed on. Okay, so you've got the sound pushing on your eardrum, your tympanic membrane, which then vibrates. That vibration causes vibration in these bones. These bones are pushing on the cochlea, which is filled with fluid, and this fluid is moving around, kind of vibrating these hairs, and these hairs are sending signals to the brain as they vibrate. And your brain is able to interpret that as sound. Okay, so there's what sound is. Sound is a compression wave in a physical medium, usually in air, but sound can also be in water, and sound can be in metal or anything else. All right, so in general, the speed of sound varies in different materials. The speed of sound varies in different materials. And there is a few factors that affect it. All right, so the elastic properties. So the elastic properties affect the speed. For instance, rubber has a very low speed. The speed of sound of rubber is only 60 meters per second. Whereas metal, with much less elasticity, and aluminum is a very unelastic metal. Aluminum is very brittle. You can snap aluminum. Aluminum has a high speed of sound. Upwards around 6,320 meters per second. So the elastic properties affect. So a really elastic material like rubber has a very low speed of sound, whereas a very rigid material like aluminum has a much higher speed of sound. Density. Density tends to affect the sound. So density also affects speed of sound. So if two objects have the same elastic characteristics, then the less dense material will have a faster speed of sound. Okay, so if you take two objects, they have the same elastic characteristics, the less dense one will have this faster speed of sound. Okay. In gases, in air, so in air you have two things. So we're going to talk about air. Temperature, an increase in temperature will give you an increase in the speed of sound. Whereas density, a decrease in density for air, a decrease in density will also result in a speed of sound, increase in the speed of sound. So at an increase in density also increases the speed of sound. So sound travels faster through more dense air. Sound travels faster through higher temperature air. So it's a little bit different than here when we're dealing with gases, because air is a gas and this is solids. Right, this one here will only be for solids because gases do not have elastic characteristics. All right, so that's complicated stuff. Now we're going to talk about decibels. Decibels is a scale to measure sound. And it measures other things. It is logarithmic. Logarithmic, which means it doesn't go up linearly. Because human ears have such a great wide variety of ability to sense different sound levels, a linear scale doesn't make any sense. So we get this logarithmic scale. All right, so decibels, how it works is like this. Decibels. I'm spelling, yep, that's right, decibel. Decibel level of 1 is the quietest sound that a typical human can hear. So think about a pin drop. That's about a decibel 1. a pin drop a little ways away from you, just so you can just hear it. That's about a decibel 1. Now, amplitude, if you remember, the amplitude of a wave is proportional to the energy of the wave. And we also say the amplitude of a wave is proportional to the loudness of the sound. So bigger amplitude, more loudness. So decibel 1 is very small. The next one is 20. At decibel of 20, this is now 10 times louder than decibel level 1. Well, you might think that's kind of weird. How come 20 is only 10 times louder? Well, every 20 that you go up in the decibel range, you go up another 10 times. So decibel 40 is 100 times louder, or 100 times more amplitude than 1. When I say louder, what I'm really meaning is a larger amplitude. It's got 100 times the amplitude of a decibel 1. So 60 is 1,000 times the amplitude. I'm going to just switch it here. So loudness of 1. 80 is now 1,000, 10,000 times the amplitude or loudness of 1. 100 is now 100,000 times this. So 100 decibels is 100,000 times this amount. 120 decibels is now 1,000,000 times. Now, up to this point here, 120 decibels is where you start to get hearing damage. Um, 140 decibels. 140 decibels is 10 million times. You can hear something that's 140 decibels, and it's 10 million times bigger amplitude than a decibel 1, which you can also hear. So you can hear this, decibel 1, and you can hear this, decibel 140. The loudness of the decibel 140 is about 10 million times that. So rather than dealing with big 10 million times numbers, 10 million numbers in 1, we just make this logarithmic scale. This is standing close to a jet engine at takeoff. Permanent hearing damage. You need to wear something on your ears or you will wreck them at 140. 120, typical ambulance siren when you're right next to it. When you're next to an ambulance siren. 100 is about a hand drill. Still, for prolonged periods of times, you want to be wearing protection for this. 60 is about a normal conversation. So when we speak about 1,000 times louder than the quietest sound that we can hear. The loudest sound possibles can be like, somewhere around 200 decibels is about the loudest sound that's possible. If you go on YouTube and you look up guys who make their they go in competitions to see who can make the loudest stereo systems in vehicles. They'll be getting up to 160 or more decibels, permanent hearing damage if they turn them all the way up. It can get quite crazy to watch them. Like, the sound is so loud, it pushes your hair around. You know, once you get up into 120 and you get some nice low bass going, like at a concert, you can feel that right through your chest. So these sounds can be dangerous. And you can see here, that's the quietest sound. 140 is 10 million times the amplitude of it. So anytime you get a 20 decibel increase, a 20 decibel increase is 10 times an increase in the loudness. Right. Now, doesn't quite work perfectly because we're more sensitive to certain types of sounds than others. So some sounds we'll hear at 60 decibels will sound louder to us than other ones at 80, just because we're more sensitive to certain types of sounds. So human hearing perception is much more complicated than just a simple scale. All right. Last thing is the Doppler effect. The Doppler effect is common with sirens. And if I draw myself a little ambulance here, there's my beautiful ambulance. It's got the big red cross on the side. It's purple. It's got the lights on top. Window, little guy driving it. My beautiful ambulance. The ambulance has a siren. Now, if that siren has a frequency. Frequency we refer to as pitch. Right, a high frequency and a low frequency. So those are different frequencies. High frequencies have high hertz levels like 2, 3, 4,000 hertz. Low frequencies, 20, 30, 40, 100 hertz. So if this ambulance is stationary, okay, so the ambulance is not moving in picture 1. Not moving. We have a guy standing here and a guy standing here. The ambulance will send out a sound at a certain frequency in both directions. Now let's say that frequency is 2,000 hertz. You can get a tone generator and figure out what that means. This guy over here will hear a 2,000 hertz sound, and this guy over here will hear a 2,000 hertz sound. So that's with the ambulance not moving. Now, we're going to get this ambulance, and it's going to be in the same spot here. Here's my new ambulance. Here's a guy right here, and he's not standing on the road, as you can see, so he's not going to get run over by the ambulance. And there's a guy standing here. Now, the ambulance is driving this way at 150 kilometers per hour. Wee, wee. Its siren is still producing a 2,000 hertz frequency. But because the ambulance is moving this way, and the source of the sound is moving in this direction, the sound waves are going to be tighter together here. And this guy is going to hear a higher pitch. So his sound is going to be greater than 2,000 hertz. There's a formula to figure out what it would be according to the speed. And this guy over here, because the ambulance is moving away from him, the sound waves are going to be more spread out. And he's going to hear a lower pitch sound. It's going to be less than 2,000 hertz. Again, there's a formula to figure this out. You don't need to know the formula for this class. So this is called the Doppler effect. The Doppler effect states that if the source of the wave is moving, the wave frequency will be higher in the direction of movement right? The direction of movement is this way, so the source frequency, so the wave frequency is higher in the direction of movement, this way, and lower in the opposite direction. Right, so the source of the wave, the ambulance, is moving this direction. So in the opposite direction, we're going to get a lower frequency wave. And in the direction it's moving to, we're going to get a higher frequency wave. You can hear that from an ambulance, or if you watch race cars, when they're coming to you, they sound higher. When they're going away from you, they sound lower. And there's formulas to compute exactly how much higher the sound or how much lower the sound will be. But that's beyond the scope of this course. All right, I hope you understand a little more about sound waves. There's your readings right here. Thank you for watching. If you have any questions, please ask.